go ahead and do the intro. Hey everyone, welcome back to second session. We're delighted to have Kunisky to give what we used to call a board talk, and then we called it an iPad talk, and now we have to go back to calling it a board talk. So take it away, Tim.
Thanks. Sorry to have to make everyone change notation. So thanks for the invitation to speak. Please tell me if I'm standing in front of things or if I'm writing too small. So everything I talk about will be joint work with John Niles Weed, who I think I may have forgotten to mention in my abstract. So sorry about that. So I'll talk about this class of problems that we studied, which is a variant of certain problems over graphs, as I'll describe, but I'll start with some more practical motivation. So we're interested in problems coming from tracking say many moving particles. So imagine here we have, space. We have particles. And particles move somehow. And we're interested in, don't know, here, etc. And we would like to keep track of this as it happens. So how do we actually, kind of observe this kind of process in practice? Well, we can think, here's time. We start at some point, and periodically we just observe the positions of these things. So we can't observe these continuous trajectories. We just take these kind of snapshots. So here, 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 and at each time, okay, I won't try to actually reproduce them, but we see some points. Here they've moved a bunch. Here they've moved some more, and so on. And I guess it doesn't look like they've moved very much. So from this, somehow there are some true trajectories here, in between. They moved somehow. This one maybe went down here and then back up. And this one did something like this. And what we would like to track is their identities between these snapshots. So this kind of pairing here. So this is the matching. That's why that's in the name of this kind of problem that we would like to infer. Okay, so from this kind of motivation, this kind of problem of learning these matchings just from frame to frame arises. And we want to answer all the usual questions. So in particular, I'll try to present in a way that stays kind of fairly close to this motivation as we'll see. But so the first question is, so let's say this is, we take some time step of length delta. And the first question is, what is the cost in the error in these matchings? So I'll be more precise in a moment. With longer delta. So if we wait longer between snapshots, how does that cause us to make more and more errors as we try to estimate this? And then, okay, the real thing everyone is waiting for is algorithms that do this well or poorly, and statistical or computational limitations on solving this kind of problem. Okay, so I'll describe kind of a model that we propose for just this one sub problem here between two frames. And I think it's actually maybe a little bit clearer to describe what we look at and then explain how prior work is kind of a natural simplification of this. So our model, and this is a model of one step of this process. So we start with, so at the earlier time, we start with a bunch of points, call them x1 up to xn. And for the sake of simplicity, we'll think of these as being just standard Gaussians. So that's the kind of toy model of where these points come from. Then we make some displacements of these with some variance. So the sigma squared is an important parameter. So these are initial. These are displacements.
In this particle tracking application, should I think of D as 3, like a video, or there are more abstract things to have in mind where D is high because I took a lot of measurements or something?
In the picture I drew here, in this example, we should think D is 2, and time is passing. And then I'll talk about all kinds of scalings of dimension as time permits. But that's one of the interesting things, is that the behavior of this kind of changes at certain ways that, so in particular with D depending on N. So D being a constant is kind of maybe the natural applied situation. And we'll talk a bunch about that. But as you let D get bigger with N, some new phenomena come up, and we'll get there too. Other questions? Just interrupt as desired. So then the later points, let's see, initial, final, are just what I get when I take these and I push them along like so. So again, here are the xi's, and we apply these perturbations to them, and we form these yj's. We don't know which one comes from which. The true thing that happened is, something like this, and we're trying to learn this matching. So how do we represent that? Well, we can say there's some hidden permutation, which I think of as drawn a uniformly random permutation. And what I observe is the x's, and then the y's permuted. And I want to recover this pi star. So this is the full kind of setup of this toy model of this kind of task. And we'll look at a particular way of estimating pi star, which is the maximum likelihood estimator. So here, you write out your Gaussian densities and whatnot, and you get that a reasonable way to estimate this is to try to minimize over permutations this kind of sum. So we just try to minimize the sum of squared distances in all ways to match these together. This is the same. We can drop all of these norm terms because each one happens exactly once. And so this is the sort of specific kind of estimator we'll look at, and this can be solved efficiently. So unlike some other situations where there are questions about, well, can we even efficiently compute this? Here we definitely can compute as a linear assignment problem. This is an optimization problem on a matrix which contains either of these two pieces of so this is just, you can think of this as a linear program, and there are more practical, efficient algorithms finding the largest permutation in this matrix. And so the question is, how well does this estimator work? So in particular, count the number of errors it makes. Define this set E of everything that it matches incorrectly. And we'll consider the number of these errors that it makes. Random variable as n goes to infinity. Okay, so this is the only estimator I'll look at. I'll maybe mention some kind of problems about whether other algorithms might do better than this, but this is the main thing to talk about. Okay, so now I'll try to write here and tell me if when you stop being able to see. Hopefully it'll all fit. So let me mention the prior work here. It differs from what we're doing on kind of two major counts. First of all, people have looked at the same kind of thing with this matrix having independent entries. And second, focusing on the threshold of so-called strong recovery, which is when the number of errors you make is little o of n versus of order n. And as we'll see, and in talking about that, we'll return to the original motivation. It might make some sense to think about the kind of finer grained behavior of this number of errors to learn something about actually solving that kind of problem over and over again. But here, kind of the main example, or maybe the one that we can analyze most thoroughly, has been, for instance, so here we should think of W as having the squared distances, and this having one of two exponential distributions. So this one is small, lambda here is a constant. So this is in the case of the planted entries. And otherwise this distance is large. And this kind of follows some work on the unplanted version of this by Parisi and then Aldous and others. Long older line of work. And here you can establish a sharp threshold for strong recovery. This happens to be at lambda equals 4. So the line of work where this was done, this kind of thing was introduced for a different set of distributions in this paper by, let's see, I believe this is Chertkov, Krok, I don't recall who V is, and then Shakala and Zdebarova, 2010. Then kind of picking up the thread, there was a paper by Chris Moore, Moharami and Shu just a few years ago, which did actually treat this model and establish this threshold. And then kind of elaborating on this and also treating other distributions, there's another recent paper of Ding, Wu, Shu, and Yang just this year. So all of these results are working under this type of model, saying where is the sharp threshold, if any, how does the kind of, in this regime here, how does the curve of how this amount of error depends on a parameter like this lambda look, and et cetera, et cetera. So maybe we'll have time to see at the very end how a certain kind of extreme version of this problem where D gets very large with n actually recovers this kind of limit. But for the most part, the kind of moral of the story will be that these geometric problems behave quite differently and have some different phenomena. So any questions of this setup? If not, I can start stating some results. Finally, let me note before that, maybe you can see here, and if not, it's not a big deal. So for us, an extra complication is that here, there's only one kind of parameter involved in in this whole problem, which is lambda, for us, we have two parameters, which are sigma squared, which depends on n, and d, which possibly also depends on n, like I mentioned before. So this is just to say that even just the description of the results will be a little bit more complicated than just saying there's a sharp threshold at some particular one value. So I'll have to describe how both of those look. Let me leave this up back here. So the first set of results concerns maybe the regime that's closest to this kind of problem. So at least make sure that I get through these. And this is when d, which can depend on n, is much smaller than log of n. And here, there will be a few natural regimes. So here I'm imagining the rate of growth of d is fixed, and I'll say properties about sigma that create different amounts of error. So these three thresholds will be sigma much smaller than n to the minus 4 over d. So the last one will be sigma at least n to the minus 2 over d, and the middle one will be in between. Alpha over d, and alpha is some number between minus 4 and minus 2. And let me draw just a picture of what the results say. So here I'll put, so let's imagine we'll work with this parameter alpha. Here I'll put that. And on the y-axis, I'll write on a logarithmic scale in n, the number of errors that I make. So here you can imagine this may be +1, so that when the error is 0, then this is 0. So here will be this threshold, lambda is -4, lambda is -2. So when the amount of noise is very small, then we can achieve perfect recovery. So here, this is only on this logarithmic scale, but the number of errors is really 0 with high probability in here. This is 0. Up here, let's say somewhere is 1. When there is a lot of noise, when sigma squared is bigger than the second threshold, then we make kind of a macroscopic number of errors. So this is that same omega of n amount of error from before. And in between here, this grows linearly with alpha. So these are the kind of main results in this regime, and you can be a little bit more precise about, well, how far from actually linear error in n is this here, and so on, but this is the general idea. So this is A, this is B, and this is C.
So the middle line doesn't depend on alpha?
The middle line here?
That slope, I mean, just doesn't.
Yeah, so this is this whole thing here is, I believe, 2 plus alpha over 2. This is the exponent of the error. So how do we argue this kind of thing and see that this is in fact what happens? So the analysis is similar to the kind of thing that those papers over there do, and in particular the one of the MMX paper. So we count the number of a certain structure in here called augmenting cycles. So this is maybe a slightly different definition than usual. say that a cycle like this, so these are indices between 1 and n, different indices, is augmenting if, kind of adding it, pushing the labels along this cycle makes the objective function better. So it augments the thing we're trying to optimize. And it's pretty easy to check that the set of errors that you make is some maximal disjoint union of these things. The incorrectly labeled indices decompose into these, and this decomposition must be maximal. You can kind of put another one in there, or it would be favorable to make that to kind of adjust along that cycle, and this permutation would not be the optimal one. So because of this, we can use first and second moment methods. To bound the number of errors above and below.
Just there, the MMX paper didn't do this second moment. That was
Right. Yes. So the kind of positive results of MMX use the first moment, meaning the ones that show that this is small. The negative results use some fancy thing following Parisi and all this, and then the second paper down there, right, use the second moment method. Thanks. Okay, so anyway, so I won't get into the details of this, but we can get an idea for why this kind of thing happens by looking at how the counts of augmenting cycles look. So let's say that the CK is the number of augmenting K cycles. And let me draw pictures of how the typical value of CK looks in these three regimes. And this will also give me a chance to gesture at some of the proof ideas. So I'll plot log, again, on this kind of log scale, the log expectation of CK over log of n. Here will be 0, and here will be K. And the cycles start with 2, 3, 4, 5, etc. So in regime A, what happens is that, so the idea is that always the two cycles will make kind of the dominant contribution, and that's what lets us carry out this whole analysis, because they're sort of small and possible to count fairly easily. So there's some kind of curve that gives these quantities, and actually computing this and analyzing it is kind of the main technical device. But here, the kind of the expected number of two cycles is polynomially small in n. So, with high probability there are none of them, and then this decreases from there. And so union bounding over all of those gives you this perfect recovery result. Now, the same thing in regime B. So here, somewhere up here is 1. Again, in this intermediate error regime, the two cycles make kind of a dominant contribution, but it's somewhere between 0 and 1 now. And again, the rest we show make an even smaller amount. So again, to count the number of errors, and okay, you have to say something about how typically these two cycles are all kind of disjoint and sprinkled uniformly among all possible pairs. But you can do that, and you'll see that this is the true amount of error that you make in this situation. So here we just do first moment, and here we do first plus second moment. And then will people see if I kind of over here? Okay. So okay, let me draw. See? So here, one of two things happens. Here, the number of 2 cycles is at or above 1. And in fact, it can either go down like this, or it can even, and this happens sometimes, go down and then go back up. And so really, there will be quite a lot of augmenting larger cycles, but still the 2 cycles make a dominant contribution. So let me say, to conclude, 2 small things about how this changes, or about why this is useful for this question and how this changes for higher dimension. So first, about this question, like why do we care about actually computing this exact exponent? So we talk in the paper about an example of n Brownian motions. So here I'm really going to go with kind of the motivation over there. And here, so in one kind of time step, how much does some xi move to yi? Well, it follows some Brownian path here. And this displacement has a variance delta. So the amount you can check from over there, the number of errors you expect to make per step is like delta to the d over 2 times n. So this is using this. And then, so how many time steps, maybe this is all I'll say and then I'll finish. Time steps to kind of decohere. So if you're trying to track all of these things, to lose track of all of them, or of almost all of them, how long does that take? Well, that takes n divided by this times steps. How much time does it take to decohere? That's the number of steps times the amount of time that passes in each step. And so this is like delta to the 1 minus d over 2 over n. So let me just admire this formula for a second and I'll wrap up. So this is assuming that the errors that you make in each time step are kind of disjoint or affecting different indices. In d equals 1, you can convince yourself that that actually doesn't happen at all. Brownian motions intersect and kind of bounce around each other a lot. But what this leads us to predict is that for d equals 2, maybe surprisingly, we actually expect there to be very little returns to sampling more and more frequently in terms of how long you can track for kind of cumulatively. So it's a little return on delta, whereas for d at least 3, suddenly this becomes a polynomial return on delta. So, and we do some numerical experiments also and verify that more or less it looks like this is what happens. So this is the main open problem, actually, not these larger dimension things. This is kind of a more practical thing that I'd like to advertise. There seems to be this interesting transition between dimension 2 and dimension 3 in terms of tracking. And here I think there are lots of interesting open problems. In particular, is this iterative computation of the maximum likelihood estimator, or in fact, you can check that you can replace it with a greedy algorithm and it'll do just the same. Is that optimal? Or is it optimal if you don't get to store a huge number of snapshots and you have to do this in an online fashion? Can you improve, in particular, on this kind of poor performance in the class of online algorithms. Okay, so thanks for your attention. When D scales as log n, there's also a surprising jump here. It's strange. Take a look at the paper if you're curious, but thank you.
So maybe one question for Tim as we switch over to the Zoom talk setup. You want to just run it?
Yeah, sure.
What regime of D do you start to recover the independent?
So I was going to talk,
Okay.
yeah, extremely optimistically about three regimes: D less than log n, D equal to log n, which is kind of an or D, proportional to log n, where this jump happens, and then once D grows faster than log n, then it behaves like the independent regime, in particular with this inner product choice of the W matrix I wrote before. It starts to look like Gaussians, either centered or with the mean shifted. And the thing you get for the MLE recovers. So the DW XY paper mentions this for Gaussians, and you get the same result as they do. But the MLE is suboptimal. You should actually use a greedy algorithm, but a particular kind of greedy algorithm, and it gets a little bit hairy.
Cool. Thanks, Tim. Next up, we have Jayadev. From the bootcamp, our experience was that for Jayadev to hear us